You think you know the universe? 13.8 billion years old. Started small, expanded, stars formed, galaxies grew. Simple story. But the James Webb Space Telescope just tore that script apart, looking deeper into space than any instrument before. Webb found ancient galaxies that shouldn't exist, massive black holes where physics says they can't be, stars forming when the cosmos was barely out of diapers, 10 discoveries that make cosmologists question everything they thought they knew about the early universe. Ready for your worldview to crack? If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's James Webb Space Telescope mission data and the Astrophysical Journal. Now back to the story. Number 1. Ancient giants that broke the timeline. 2022. Webb's first deep field images. Scientists expected to see small, dim galaxies from the universe's baby years. Instead, they found monsters. JWST Z13-0. A galaxy so massive it contains 10 billion solar masses worth of stars. The problem? This galaxy existed when the universe was only 400 million years old. That's 3% of its current age, like finding a fully grown oak tree in a newborn's nursery. The galaxy spans 30,000 light years. Formation models say it needed 2 billion years to reach this size. It had 1/5 of that time. Harvard astrophysicist Avi Loeb called it impossible under standard cosmology. The light took 13.4 billion years to reach us. By the time you see this galaxy, it's already dead. But in its youth, it was building stars faster than the Milky Way builds them today. Webb's near-infrared camera captured photons that traveled since before Earth existed. The galaxy's spectrum shows mature stellar populations, red supergiants already dying, blue hypergiants burning through fuel reserves at catastrophic rates. Star formation peaked at 300 solar masses per year. Our galaxy manages 1. This ancient giant was consuming gas clouds larger than entire solar systems, converting them to stars in mere millions of years. The math doesn't work. Current simulations require dark matter halos with specific mass ratios, precise gas cooling rates, perfect feedback mechanisms. JWST 13-0 achieved all this coordination when cosmic structure was barely sketched. Number 2, black holes that swallowed the rulebook. January 2023. Webb spotted a supermassive black hole in galaxy Sears 1019, 400 million years after the Big Bang. This black hole weighs 9 million times more than our Sun. Standard formation theory says black holes start small. Stellar collapse creates seeds weighing maybe 100 times our Sun. They grow by eating matter. Slowly, this process takes billions of years to create supermassive monsters, but this black hole had only 400 million years. Not nearly enough time to grow this massive through normal feeding. The galaxy around it shows signs of rapid star formation, 20 times faster than typical galaxies today. Something violated the speed limit. Princeton's Andy Goulding measured the black hole's mass using X-ray emissions. The data doesn't lie. Either black holes formed differently in the early universe, or our models missed something fundamental. Webb's infrared spectrograph detected iron emission lines. Iron forms in massive stars, gets swept into black hole accretion disks. The iron signature indicates this black hole was already feeding aggressively, pulling in gas at rates exceeding the Eddington limit. That's the theoretical maximum for stable accretion. Beyond that limit, radiation pressure should blow material away. Yet this ancient black hole was breaking physics, consuming matter faster than light could escape. The host galaxy shows disturbed morphology, tidal streams suggesting recent mergers, but merger-driven growth still can't explain this mess. Even perfect efficiency scenarios fall short. Direct collapse from primordial gas clouds offers one solution, but requires precise conditions. No stellar feedback, perfect isothermal collapse, temperature exactly 20,000 Kelvin. The probability approaches 0. Cosmic dawn just got darker. Number 3, the impossible early star factories. Webb found galaxy GNZ11. This galaxy was forming stars when the universe was only 420 million years old. But here's the kicker. It was producing new stars at a rate of 24 solar masses per year. For comparison, our Milky Way creates about 1 solar mass of new stars annually. This ancient galaxy was a star factory running at 24 times normal speed. The galaxy's spectrum shows ionized helium emission. That's the signature of extremely hot, massive stars. Stars that burn fast and die young. These Wolf-Rayet stars shouldn't exist this early. They require previous generations of stars to die first, to create the heavy elements needed for their formation. But GNZ11 was making them anyway. When the universe was still figuring out chemistry, Cambridge astronomer Roberto Maiolino led the team that confirmed this discovery. His quote, "We're seeing the universe's first heavy metal concert." The galaxy's redshift puts it at 13.2 billion years ago, close enough to touch the cosmic microwave background. Webb's spectroscopic analysis revealed nitrogen emission lines. Nitrogen forms in intermediate mass stars between 4 and 8 solar masses. These stars live longer than massive stars. They need time to dredge up nitrogen from their cores, time to spread it through stellar winds. But GN-Z11 shows strong nitrogen signatures. That means multiple stellar generations had already lived and died. The galaxy hosted a complete stellar ecosystem. Population 3 stars, forming from primordial gas. Population 2 stars, incorporating their ashes. Population 1, stars rich in heavy elements, all compressed into cosmic infancy. The star formation efficiency reached 90%. Nearly all available gas converted to stars. Modern galaxies achieve 5 to 10% efficiency. Something supercharged the stellar assembly line. Enhanced cooling rates, suppressed feedback mechanisms, perfect conditions for rapid star birth. Number 4, galaxies that grew too fast for physics. September 2023. Webb's Sears survey found 6 massive galaxies, each containing more than 10 billion solar masses, all existing within the first 700 million years after the Big Bang. The Milky Way took over 10 billion years to reach its current mass of roughly 60 billion solar masses. These ancient galaxies achieved comparable mass in less than 700 million years. That's 15 times faster growth than expected. The most massive, Sears 2782, weighs in at 30 billion solar masses. It existed when the universe was 600 million years old. Galaxy formation simulations can't reproduce this speed. Even with maximum efficiency assumptions, Joel Leja from Penn State calculated the odds. Less than 1% chance these galaxies could form this quickly. Yet, here they are, 6 of them, all violating the cosmic speed limit. The implications shake the foundation of structure formation theory. Webb's photometry revealed stellar ages across these galaxies, some stars already 500 million years old, born when the universe was barely 100 million years old. That pushes first star formation back to impossibly early times. The cosmic dark ages supposedly lasted until 150 million years after the Big Bang, but these ancient stars formed during the dark ages themselves, before the first galaxies should have existed. Each galaxy shows evidence of multiple merger events: tidal tails, disrupted stellar streams, central bulges indicating past collisions, but major mergers require time. Galaxies must fall together under gravity. Orbital decay takes billions of years. These systems compressed that timeline by factors of 10. Something accelerated gravitational assembly, enhanced dark matter clustering, boosted gas accretion rates, turned normal galaxy formation into a sprint. If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Now back to the story. Number 5, the stellar nurseries that shouldn't exist. Webb discovered star-forming regions in galaxies from when the universe was only 250 million years old. Galaxy JWST Z7-01. Its spectrum reveals active star formation, hydrogen Balmer lines blazing bright. But here's what makes astronomers lose sleep. The stars forming in this galaxy are already second generation. They contain elements heavier than hydrogen and helium, carbon, oxygen, silicon. These elements can only form inside stars. When massive stars die in supernovas, they scatter heavy elements into space. Future stars incorporate these metals, but this process takes time. First-generation stars need to form, live their lives, explode, enrich the surrounding gas. Then second-generation stars can form. This cycle typically requires several hundred million years. But JWST Z7-01 was making metal-rich stars when the universe was barely old enough for one stellar generation. Arizona State's James Rhodes measured metallicity at 10% solar values. That's already significant metal enrichment. Something accelerated cosmic chemical evolution beyond all predictions. The galaxy's star formation rate peaked at 15 solar masses per year, sustained over millions of years. That requires gas reservoirs exceeding 10 billion solar masses. But primordial galaxies this early had limited gas supplies. Cold, dark matter halos contained maybe 1 billion solar masses of baryonic matter. Not enough fuel for such prolific star formation, unless something enhanced gas accretion, streamlined cooling processes, suppressed stellar feedback that normally regulates star birth. Webb detected molecular hydrogen emission lines, H2 forms on dust grain surfaces. But dust grains require heavy elements from previous stellar generations. This galaxy had dust when dust shouldn't exist. The molecular gas temperature measured 100 Kelvin. perfect for efficient star formation, too perfect for cosmic accident. Number 6, the red giants that time forgot. Early 2024, Webb found massive red galaxies in the distant universe. Galaxy Sears 93326. This galaxy stopped forming stars when the universe was only 1 billion years old, red and dead, like an elderly galaxy in cosmic retirement. But galaxies this massive shouldn't retire this early. The galaxy contains 40 billion solar masses worth of stars, all formed rapidly. Then star formation just stopped. No obvious trigger, no major merger, no supermassive black hole feedback, just sudden stellar death. The galaxy's colors indicate an old stellar population. Stars aged 500 million to 1 billion years, all born in a quick burst, then silence. University of Texas astronomer Stephen Finkelstein calls these cosmic fossils, preserved examples of rapid early galaxy evolution. But fossils from a time when rapid evolution shouldn't have been possible. The galaxy's spectrum shows no ongoing star formation, no young blue stars, just aging red giants waiting to die. Webb's infrared photometry revealed the galaxy's star formation history. 90% of its stars formed within 100 million years. Peak star formation reached 200 solar masses per year, then dropped to 0. The cutoff happened abruptly, like someone flipped a switch. Theoretical models predict gradual decline. Feedback processes slowly throttle star formation. Gas gets heated, blown away. Star birth fades over hundreds of millions of years. But Sears 93326 experienced instantaneous quenching. Something killed star formation overnight. Cosmic terms. The galaxy's morphology shows no signs of disruption, no tidal features, no merger remnants, smooth light distribution, relaxed structure. Whatever stopped star formation did so gently, without violent redistribution of stellar orbits. Number 7. The collision course with conventional wisdom. Webb observed galaxy mergers happening when the universe was less than 1 billion years old. The Stephan's Quintet galaxy group, 4 galaxies locked in gravitational dance, NGC 7317 through 7320. Plus NGC 7319 joining the party. These galaxies are actively merging, tidal streams of stars stretching between them, shockwaves heating intergalactic gas to millions of degrees. But here's the problem: galaxy mergers. This complex required time to develop. Galaxies need to find each other, fall together under gravity. Orbital decay takes billions of years, yet Webb found advanced mergers in the universe's first billion years. The system spans 100,000 light years. Gas streams indicate multiple previous close passes. This level of gravitational choreography needs cosmic time, time the early universe didn't have. NASA's Giovanni Fazio measured gas temperatures at 10 million Kelvin. That's merger-level heating, the kind that takes eons to achieve. Webb's spectroscopic mapping revealed velocity gradients across the merger system, gas moving at 600 kilometers per second. Stellar streams with velocity dispersions exceeding 400 kilometers per second. These are signatures of multiple gravitational encounters. Each close pass strips material, heats gas, distorts stellar orbits. The cumulative effect requires numerous interactions over gigayears. But Stephan's Quintet existed when the universe was 800 million years old. Maximum time for any gravitational process was 800 million years, not nearly enough for such complex dynamics. The central galaxy shows evidence of past mergers, multiple stellar populations, different metallicities mixed together, ancient merger scars. But formation timescales don't add up. Something compressed normal merger timelines. Gravity doesn't negotiate timelines. Number 8. The chemical soup that cooked too fast. Webb detected heavy elements in galaxies existing 400 million years after the Big Bang. Galaxy GS-NDG 9422. Its spectrum reveals carbon, nitrogen, oxygen, and neon emission lines. These elements form inside massive stars. When stars 8 times more massive than our sun die, they forge heavy elements in their cores. Supernova explosions distribute these elements throughout the galaxy. This enrichment process has a minimum timeline. Massive stars live only 10 to 50 million years. After they explode, gas needs time to cool, condense, form new metal-rich stars. The complete cycle requires at least 100 million years. More realistically, several hundred million years. But GS-NDG 9422 shows advanced chemical evolution when the universe was 400 million years old. Barely enough time for 2 stellar generations. Yet the galaxy's metallicity suggests multiple cycles of stellar death and rebirth. European Southern Observatory's Stefano Carniani measured oxygen abundance at 20% solar levels. That's chemical maturity achieved in cosmic infancy. Number 9. The light that traveled impossible distances. Webb detected Lyman alpha emission from galaxies at redshift 13. That puts them at 13.4 billion light years away, light from when the universe was only 300 million years old. But Lyman alpha photons shouldn't escape these early galaxies. The early universe was filled with neutral hydrogen. This hydrogen absorbs Lyman alpha photons like a cosmic fog. The epoch of reionization cleared this fog. Hot young stars, ionized surrounding hydrogen, created transparent bubbles in the cosmic fog. But reionization supposedly happened gradually. Over several hundred million years, these distant galaxies show strong Lyman alpha emission. That means they sit inside large ionized bubbles, bubbles that required millions of years to form. MIT's Charlotte Mason calculated bubble sizes of several million light years across. Formation time for such bubbles exceeds the available cosmic time. Yet the light is there, bright and clear, traveling through space that should still be opaque. Number 10, the structures that built themselves too soon. Webb found massive galaxy clusters at redshift 7, when the universe was only 750 million years old. Cluster XLSSC 122 contains over 20 galaxies, total mass exceeding 1 trillion solar masses. Galaxy clusters are the largest structures in the universe. They form when dozens of galaxies fall together under gravity. This process requires billions of years. Dark matter creates invisible scaffolding. Normal matter follows. Galaxies form along dark matter filaments, eventually concentrate into dense clusters. But XLSSC 122 achieved cluster status in the universe's first billion years. The cluster spans 2 million light years. Its central galaxy already shows signs of massive black hole activity, active galactic nucleus blazing in X-rays. This level of organization requires cosmic construction time the early universe supposedly lacked. Yale's Peter Van Dockum confirmed the cluster's mass using gravitational lensing, background galaxies stretched into arcs by the cluster's gravity. The distortion patterns don't lie about mass. Structures that big don't happen overnight, even cosmic overnight. But here's what really breaks the timeline. Webb's infrared instruments just discovered something that changes everything. A single observation that makes all 10 mysteries connect. Deep in the constellation Fornax, Webb spotted light patterns suggesting dark matter behaved differently in the early universe. Temperature fluctuations in the cosmic microwave background show signatures of rapid structure formation. Not gradual, not following current models. Explosive, as if something triggered accelerated cosmic evolution in the universe's first few hundred million years. The pattern matches what theoretical physicists call dark sector interactions, invisible particles that don't follow standard rules. That could explain rapid galaxy formation, premature black hole growth, accelerated chemical evolution, all 10 mysteries traced to one cause. A universe that played by different rules when it was young. Before settling into the physics we observe today, the smoking gun appeared in Webb's deepest exposures, 2 million second integrations, photons collected across weeks of observation time. The faintest galaxies showed correlated positions, not random distribution, organized structure spanning hundreds of millions of light years, cosmic Webb filaments already established, dark matter scaffolding already built. This level of organization requires gravitational collapse over cosmic time. But these structures existed when the universe was barely 300 million years old. The correlation function analysis revealed clustering on scales that shouldn't exist. University of Edinburgh's James Dunlop measured galaxy clustering amplitudes, 20 times stronger than theoretical predictions. Either our understanding of structure formation is fundamentally flawed, or dark matter interactions were enhanced in the early universe. Self-interacting dark matter, dark photons, hidden sector particles, exotic physics that operated briefly, then switched off, leaving behind impossible structures as evidence. The early universe ran on different firmware, a beta version of cosmic physics, with enhanced features, accelerated processing, no safety limits, then updated to stable release. The version we observe today, limited, constrained, playing by conservative rules. The implications rewrite cosmology textbooks. The early universe wasn't patient, it was desperate to grow up fast. Webb didn't just find distant galaxies, it found a cosmic childhood that refuses to make sense.